Okay, everybody can hear me. So good afternoon. So today, for the next discussion, we're going to be talking about the path effects that are relevant to the Palo Verde nuclear power plant. And in particular, these path effects are, as we saw yesterday, are from the distant sources in California that contribute to the hazard, that are the primary contributors. So initially, I'd like to invite Kevin Mayeda to give his talk on the path effects.
Okay, thank you. Can everyone hear? So my name is Kevin Mayeda. I'm at UC Berkeley, and I was asked by Carola and Norm to discuss some lateral attenuation studies that Scott Phillips, myself, and Luca Valentini did earlier last year, and it recently came out. So this is my one and only reference. So a few of the questions that came up to us were essentially to comment on regional variations between the Palo Verde area and perhaps Southern California in the Diablo Canyon and Salton Trough areas. And I guess just a point of clarification, the Q maps and whatnot that I'm showing you are actually based on regional LG. These are not local S waves. There are some local S waves that are included in these inversions. So some of you have probably seen, which one is the laser pointer? So what I'm going to show you here first is just a map of LG essentially centered at 1 hertz. This is obviously western US, and 6 to 12 hertz. And not surprisingly, at the shorter wavelengths, we see a lot more structure. The other thing that's very interesting too is at the longer periods, we clearly see the Great Plains, we see the Colorado Plateau, we see the Great Basin, Sierra Nevada. But to really look at variations here and here, we really need to zoom in. Okay. This is just another summary slide as well. We've attempted to fit the frequency-dependent Q with the power law, and that seems to work pretty well throughout the region. What we're showing here on the left is Q naught, and even though this thing says 200, we're actually getting Q naughts here near the Diablo Canyon area around 70. And the same is true for the Salton Trough area, pretty low. Now, keep in mind, these are LG-derived Qs with an assumed geometrical spreading. Now, how they correlate to the direct S-wave Q, that's a matter of debate and research. But I think...
I think for Palo Verde, aren't we after LG anyway? I mean, we want the biggest, whatever the biggest waves are going to be.
Although I did hear somebody say something about a fault that was located right next to it.
There we don't have to worry about Q. We have other problems.
Yeah, you got bigger problems than that.
So I think this is just what we want.
Right. All right. And again, because we're fitting this power law, this is the eta term that's the frequency-dependent part. And again, if you look at those of us who lived around here, this map makes sense geologically, geophysically. Okay, so now kind of zooming in. I actually had Scott do this because the other great thing is because Scott did the inversions, I can blame him for any issues that come up. And I absolve myself. So what we did is we looked at some paths coming from Tage, which is in the kind of north of the Phoenix area, and then looked at Landers, which is kind of the northern part of the Salton Trough, and we could also do something right at Diablo Canyon. So the 2D model exists. I think Scott has readily given out the model, and you can go and integrate 1 over Q to your heart's content and look at azimuth dependencies. Okay. This is an example of, and Carola had asked me to look at relative differences between amplitudes both at Palo Verde and kind of the north of Salton Trough area at 300 kilometers. So let me try to explain this figure. So what we're plotting here is just the log amplitude ratio as a function of frequency. So this is 1 hertz up to 10 hertz. And this is based on our model. So what we're showing you is the amplitude of essentially for, I lost the color, Phoenix area and relative to I'm sorry, Page, right, sorry. And so essentially what this is showing you here for Phoenix, there's really not a huge difference between that and Southern California. Up to maybe at 10 hertz, you're getting about a factor of 2 in amplitude, which isn't that significant. But when we look at Page, for example, the amplitudes are significantly larger. So paths that are going through essentially parts of the plateau are going to be essentially unimpeded, well not, they're impeded, but not as impeded as they are if they were to go through a lower Q part of the crust.
Kevin, can you,
Yeah.
so I'm lost here, amplitude ratio of what? Can you tell me what's?
It's relative to Landers. So this is essentially, this is...
So if it's 0, then it's the same as in Landers.
Right, so 0 is 1.
Okay.
Right, so because this is log amplitude.
Okay.
Sorry, I
That's
screwed
fine.
up
So
in the beginning.
0 is a Southern California type of model.
Right. So here, essentially, from 1 to about 4 hertz, one could argue that the amplitude at 300 kilometers for Arizona or the Phoenix area relative to the kind of Landers area, it's pretty similar. It only changes when you get up to the higher frequencies. We're just showing this as an kind of an n-member case. Here for Page, which is part of just kind of on the edge of the plateau, we can see very large amplitudes, and it's just because of the Q effect. Okay. Keep in mind, too, that we've kept the geometrical spreading the same for everything. It's 0.5. And one could argue that, well, maybe it varies, but people have done sensitivity studies in a number of areas, and 0.5 for LG is pretty good, R to the 0.5. Like I said, we do use local S waves, but it represents probably less than 5% of our total data. There are roughly, I want to say, looking at the paper, there were about 500,000 amplitude measurements, 800 stations, and so we have tremendous coverage in this area. But again, it's very regional. Okay. So one of the impacts of the Q difference, obviously, is you're going to get big amplitude differences potentially, especially at regional distances. So what I'm showing you are amplitude, log amplitude as a function of distance for different Q models from what we derived for the Western US. And this yellow band is essentially just a band from 250 to 350 kilometers. And this Q of 100, I would say, let's say, is comparable to what we get in some parts of Southern California. This is Q naught. Whereas in some parts of Arizona, especially paths that are coming from the north, that Q naught could be up in the 400 range. So here we're talking about almost a factor of 10, not quite, in amplitude at this frequency band. And of course, we could do this for a number of different frequency bands as a function of azimuth. But if you go back to this figure, I think the issue, to my understanding, is that if you pick any point here in Southern California as a function of azimuth, we're only going to see Q variations on the order of maybe 20, 30, 40%. Whereas if you're in the Phoenix area, close to where Palo Verde is, especially at regional distances when we're looking at 200 to 300 kilometers, there's tremendous azimuthal variation. I don't know where the sources are, that's not my thing, but clearly if the sources are here, they're going to behave differently than if the source is here at Palo Verde. And that's just a strictly qualitative kind of hand-waving argument, but I think it makes sense. I mean, keep in mind these inversions that were done throughout this whole area were constrained with moment tensors from Bob Herman's extensive catalog, Doug Drager's extensive catalog, And so when we do the inversion, we have to get the long periods right, and we also had apparent stresses of selected earthquakes that were done independently, and we had to nail those also in the inversion. So there's a lot of internal consistency that went into this. Now, whether or not that Q maps directly into the S-wave Q locally that you guys need, I don't know. But from a regional standpoint, I think this is fairly representative of the differences you'll see between the two regions.
I'd again say we don't need the local Q.
Okay.
So I think the regional value is exactly what we're trying to get at, and in particular, an azimuthal path going through the Salton Trough versus something more northerly. Those are going to be the sources. It's just from the big California faults there. So I think your data is exactly the data we need, for trying to figure out how do we adjust our ground motion models from California to Arizona, either empirically looking at actual ground motion amplitudes or through a model of what are the Q differences.
Right.
No, you were saying through the Salton Trough, but it seems like there are some sources that we have down in Mexico, right, that we need to worry about as well for Arizona? That path?
So
Melanie is shaking her head no. I think the main ones were either through the Salton Trough or a little bit to the north of that. To the south, yeah.
let's see if I can try to do this. Let's see, Phoenix and Palo Verde more or less here, but the Cerro Prieto is just on the around here on the kind of northern part of the Gulf of California, if I remember correctly. So this would be a part that would be important. And actually, I have a map. Oh, it's down there. Yeah, I blew up that portion of the map to show that area a little bit better. So we'll see that later. But that's those are the key areas, and I think we should. And again, the data are there from you guys. We could integrate 1/Q over those particular paths related to Cerro Prieto and related to the closest approach to the San Andreas, and then get real numbers. Because at this point, we're just looking at colors and being very qualitative, all of us. You'll see how qualitative I am later.
You said Scott has all those numbers that we can use.
Yeah, and I think it's distributed.
Yeah, in fact, I have those numbers.
Yeah.
Adrian got them from Scott,
Yeah.
and I have them from Adrian.
Good.
Any other questions for Kevin? So, and Gabe is up next trying to take this and apply it, right?
Correct.
Okay.